We have proposed a project known as the wireless stereoscopic motor-driven camera arm using Oculus gyroscopic feedback. The idea of this device is to be situated on a movable vehicle, such as an aerial drone, search and rescue device, or similar device. This will be mounted, the pivot arm that is, onto the drone in a safe location. The motor pivot arm will then be allowed to move based on a command sent to it from its host device. The cameras will be feeding back down to a separate device, which will allow the Oculus Rift to be updated with visual imagery, so the person who is viewing for the Oculus can move their head in relation to where they want the cameras to go. We assume that this form of interaction with the user will allow a much greater understanding of how the person moves the cameras in a different environment, allow greater connection to the host and the driver of the vehicle while being used in search and rescue and other different opportunities.
It was important that the device needed to be embedded so that there was portability. The Oculus Rift is quite a fairly large headset and kind of needs to be fixed at a single location. It's also quite power intensive, so it needs to be able to be supported by a power system. Batteries would not be particularly viable for the Oculus system, as if that combined with a single board computer would drain far too much power. But the image capture, Odroid, would be a lot better for a battery type operation, and generally these are also contained within the mobility device, whether it's a drone or a remote control car. They generally come with some form of battery power, and so I believe it only takes 5 volts to run the Odroid, and so we would be able to support it using a portable power system.
Okay, now you may wonder how the system works. The system is designed to be simple and effective when used. The first most important thing is to deal with the camera-driven Odroid. This is our first Odroid, Odroid 1. It's connected by USB port to 2 cameras, Microsoft Life HD 3000 cameras. These are then inputted to the USB devices, which are loaded using OpenCV to take the images and begin operations on them. At this point, they'll be appended, combined, and saved down to the file, ready to be sent down as an image file directly to Odroid 2. Odroid 2 will immediately put this out straight to the Oculus display, which displays to the user what the actual cameras are seeing. From this point, the Oculus Rift will have haptic feedback, or gyroscopic feedback, which will go into a HMD quartz function. This will return the real-life location and data of the headset. This will allow the headset data to be used for the pivot arm text file. This will be going down for into a text file, say, and sent over to the secondary Odroid dealing with motor shield. The Odroid 1 will take the data, convert it into commands that can be used on the motor shield, and send it to the motor shield on the bottom of the Odroid, which is an Arduino shield. This will be then sent to the motors with the instructions. Motors will then follow them. This will then change our pivot arm's location, sideways, up, down, left, right, depending on how the pivot arm moves. This again will then move the tail of the cameras, and the cameras will be captured and moved again, all in a real live or real streaming environment. The Odroids we're using are Linux distribution ARM course. There will all be keyboards and mice for the development cycle. When that finishes, they'll be removed so that these can be run automatically using bash scripts. We're using a wireless LAN network to connect to, using Wi-Fi systems, or Wi-Fi if you're not unsure what Wi-Fi is. And we have some other future implementations that my colleague will cover for you now.
So primary applications that we're considering would either be for military use, for surveillance, or for search and rescue. We've also considered that currently we are using a remote control car, and it's mounted onto that. The use of Steadicams, such as GoPros, would be quite useful. It wouldn't take too much implementation changes to support a different type of camera. The Oculus Rift can basically provide 6 degrees of freedom, which means that it can both rotate and move in 3 dimensions. This is supported by the motors, which have can rotate around the x-axis and the y-axis, and the remote control car can obviously move forwards and backwards and left and right, and this gives us our 6 degrees of freedom.
Okay, now you may be wondering why we use each particular device. Now, the first we'll be using is Odroid, the main device we're using. The reason we're using these, they're low power, they're relatively high performance, and should be able to suit our needs quite usefully. They also provide up to 3 USB ports, more than excess what we need for each device. With this being said, they also run Linux operating systems, Linux operating system being free and open source, and also run several high-performance tools. Since the stripped-down operating system, it will run more efficient than Windows, thus providing more performance. We're using Oculus Rift simply because of marketability. Oculus is a growing brand, VR is getting bigger every day and everywhere you see it growing. By using this, we can not only immerse our users in a practical environment with the device, such as a work environment, but we can also make sure you meet the market requirement for something that's not only practical, but usable for every day and enjoyable, so it's familiar to the user. We are also defending the right for using the motor shield on the bottom of these things, simply because any perform motor shielding would require extra programming. With the motor shield on the bottom of the Odroids, which are Arduino based, these can directly provide impulse power through a native pins on them to the device, which cuts down the requirement to use extra hardware and cost of the project. The pivot arm we've used, the mechanical pivot arm powered by two motors. We use that simply because of the fact that it's already designed, it already works, and all we need to do is program it to function, something that should make it much easier for us to work overall. That's our main justification for doing this work, and thank you for listening. We hope you enjoy the rest of the presentation. Okay, for our project, what we've been doing is implementing something called OpenCV, which is the Open Computer Vision Library. Now, we've been dealing with the main function of this, which is the Open CV's video capture / display functions. What this allows us to do is take living live feed images from 2 webcams, put them down into the Odroid, and then work on them from there. And the first part we need to do here is grab the images using dual webcams. The idea is, if I just jump past the screen here, we have 2 cameras up here. These are going to our single board computer here, or SBC for short. What these will do, they'll pick up their live feed images, they'll sequentially send them into the SBC, the code will automatically grab each frame and store it as a map type vector. What a map matrix does is essentially very similar to a 2D matrix, which works this way. Each section holds pixel data about each part of the image, which goes down to the colour parts, if it's RGB for instance, between values of 255 and 0 for 3 different sections of the image, so part of the matrix. What we can do is store it into these files here, and then we can operate on them. By knowing the basics of how the matrices work, we can append 2 matrices together, which is when we, again, apologise for the movement, have the two draw images. What we can do is take both images, take the original matrix locations of each image here and here, so we want the height and width. What we can then do is increase a new matrix, double the height and width of both of these, well, not the height, but the width, and we can import both of these directly into the new matrix. When we save this down, it becomes a singular file, allowing us to store the data more effectively. Now, once that's done, we can then save it down to the SBC and send it. Once it's sent, it can move on to an Oculus Rift display, and we'll display to any users who wish to see video from our files. Okay, in this part of the project, we're going to show you how our implementation works in a conceptual diagram. Now, first of all, I'll ask my friend George here to come closer and turn the viewpoint onto the Oculus Rift. For this, we've removed the lens of the Oculus Rift, so if you just moved it, there we go. This allows us to see the screen that's native behind the Oculus Rift. As you can see, when I move the mouse around, we can get a picture of me in parallel. Now, you won't see this how it would actually look to a user, because that's nearly impossible to do on a computer screen, but you're all welcome to try it. What it shows, though, conceptually, is that we can have images loading side by side via the mount onto the screen, which gives us a lot more scope to use it as it's intended with the Odroids. Now, of course, you can't see this part of the thing, but wearing this device, I can see this one singular item at a time as if it was being seen normally, which is the aim we're going for here. We can now see a nice recording of George himself. Well, his shirt anyway. This is a side-by-side screen using OpenCV that provides a side-by-side appended image using 2 cameras. As I move the mount around, we'll see varying different scenes based on what the cameras are moved towards. This is a side-by-side image. Now, George will move over, we'll see the mount. This mount has been forged, currently, having polyester and polystyrene. The idea of this mount is a temporary mount before we can mount on the pivot arm. Ideally, the pivot arm will be attached to the base about here. A small cutout will be made, and it will just slot straight down top of it. The part here has been cut away, so there's alluviation here, so it can bounce and rock surface on its own, without the camera being obstructed by its vision. As you can see, each camera is looped with a wire around each part of its mainstay, making sure that it's linked in correctly. The wires are then cut into a groove inside the central bar, which they wrapped around and then stuffed with a polystyrene to give a strong lock. The wires then tied at the back with a cable lock at the back, making it nice and secure as you can get. Now, if you're interested, the code is over here. The run system. Essentially, all this is a small little bit of code that basically just says, grab the camera image from that side, grab the camera image from that side, sync together in one image, and then display them to the screen, which is then routed by an HDMI connection directly into the Oculus, which is then powered straight into the Oculus so we can see everything we're doing. And that, my friends, is how we have connected 2+ side-by-side image for Oculus Rift.
So the Oculus provides haptic feedback in what's known as a quaternion. I'll explain what that is in a moment. A quaternion, in essence, is an efficient numerical system for describing movements in 3D space relative to an origin. It's intuitive to imagine rotation in the context of rotating around X, Y, and Z axes, but you run into problems with this because the order in which you rotate them affects the final position. Quaternions mitigate this problem. Due to the lack of usage of quaternions in any standard libraries, there's no concurrent usage for them, and there are many competing C libraries that are made to process and define quaternions, and this makes manipulating them quite difficult as they don't fit to standardization. One library that we tried using was OpenHMD, which is an open library for head-mounted displays that is aimed to be used for either the Oculus Rift or any of its competitors. It was a Linux-friendly implementation, primarily written in C and C++, and it resembled the Oculus library. However, it was missing some core functionality, so we tried bringing in some OpenGL functions that would help us manipulate the quaternions. This didn't work because they used the standard of WXYZ, whereas OpenHMD was using XYZW. This lack of compatibility was quite ingrained into the library, which made it quite difficult for me to go back and simply reassign the values because they were consistently referenced by other helper methods. Eventually, I chose to use libovr NSR, which is a fork of libovr, which is the standard library that the Oculus uses to expose its information. This is a pure C implementation of libovr, and it's therefore very Linux friendly. It came with all of the linking pre-compiled, and so I was able to implement it to the ARM core. Using this, I was able to extract haptic information. I'm now going to present a demonstration of the OpenGL example, which shows interfacing with the haptics through the Oculus Rift, and then I'm going to show a simple text file readout which demonstrates that I would be able to use that information to convert the Euler angles to interface with the motors. I'm now going to demonstrate the haptic feedback program that receives information from the Oculus Rift and returns it as several quaternions, which is then converted into Euler angles. As you can see on the screen is currently a display that shows the orientation. This is referenced in accordance with the Oculus Rift. As you can see, as I move the Rift, it changes the orientation of the arrow on the screen. There's some latency, which demonstrates a problem that we ran into keeping it synchronized with the motors. This is largely down to hardware restrictions, both from the Oculus Rift DK1 and the Odroid. In accordance with the block diagram, this demonstrates that the Odroid is acting as a centralized hub. The micro HDMI lead here connects to the Oculus Rift development kit, which in turn outputs a display to the Oculus headset. The Oculus headset then provides information in the form of quaternion using its gyroscope, magnetometer, and accelerometer in order to feed back to the Odroid, which in turn uses programming on a virtual Linux environment to provide usable information.
Okay, so the Oculus Rift provides haptic feedback using a gyroscope, a magnetometer, and an accelerometer. All of this information is eventually output into what's called a quaternion. A quaternion is a measurement in 3D space using just 4 values. The Oculus Rift device constantly iterates through a performance loop, and every time it does this, it outputs to the library a new quaternion. Every single iteration of that loop, I store a quaternion and then use the new quaternion in the next, when the loop iterates, to calculate the difference between 2 quaternions through subtraction. I then store this as a third quaternion and then use the get Euler from quart function that's provided by OpenGL utilities function, and that produces me with a Euler value, which is an x, y, z angle, as we would normally consider them, change in difference. This is then fed back to the motors and synchronized so that the motors face in the direction that the head-mounted display is currently facing. There can be some latency, but eventually it synchronizes as it gets to the most recent value.
Hello, my name is Kamil. As you might have a good idea by now, what is the goal of the project? It was a fantastic opportunity to work with very talented people and premium hardware, and I will do my best to explain to you progress which has been made in terms of communication between Odroid and Arduino I/O Shield. So let's get to the point. Problem which awaited me was small but tricky. It involved large amount of research, but it was necessary to control motors which move ARM with high precision. Luckily, Odroid was supplied with Arduino input-output shield, which is equipped with motor controller. Once that was uploaded, it needed external piece of software called processing, which is a computer language in itself, and it was used to communicate with Arduino I/O Shield and designed to be able to read data from a text file and then send it further to the motors. It was achieved using JavaScript. This is it for now, and my colleague will continue to explain it further. Thank you for attention.
Hello, my name is Wesley, and on our project I had the pleasure of programming the motor shields. Basically, the motor shields, the pan motor directional, the pan tilt directional motors, the motors that the camera was going to be mounted on, since the project requires a user to wear an Oculus Rift. When they look left, the camera should look left. When they look up, the camera should look up. And if they look on the right, the camera should look on the right. Likewise, if they look down. So basically, these motor shields, they had to read the data from the Oculus Rift, so that when that movement happens, those the motors would listen to the signal that's being passed by the Oculus Rift itself. To do so, we had to get some values from the Oculus Rift, pass them through to the motors using Odroid and Linux. So originally, I was going to do it using the code, Linux code, to program the motors themselves so that they can be ready to receive the data from the Oculus. But then it turned out that this was really cumbersome to use the Linux itself to read those values, because I wanted to test the motors themselves for the directions to get the angles, so that when the user looks that way, it's 180 degrees. When they look straight, it's 90 degrees, and to the other side, it's 180 degrees as well. So those degrees have to be programmed first. So before the actual values can be read, so that when the values come into the code, it's easier to program the whole scenario. But then, as using the Linux was cumbersome, I ended up using the Arduino Shield. I took advantage of the Arduino Shield, which is on the Android, and the testing itself of the motors, because I had to test the direction and program the degrees on there. I had to use the keyboard, the direction of the keyboard, the pressing of up, down, left and right. So I wanted that data to be input into the motors first, see if the motors can respond to that. So basically, as I said, I took advantage of the Arduino Shield on the actual Android itself. And for the Arduino to get the directions from the keyboard itself, processing had to be involved. So this is a development environment called processing, which reads the serial input. And the Arduino also uses the serial input. So basically, these two would have clashed. But then the good thing is the Arduino itself, it takes in the value, it takes in the code. When you program it, it keeps the code inside it, which was an advantage. So while that takes in the code, I was able to use the serial for the processing. And they both use the serial. The directions, essentially, they both worked. I mean, all four directions, up, down, left and right. And essentially, the cameras themselves could have used the directions using the keyboard in case we're unable to read the data values from the Oculus. So what would have required is the user just to put the Oculus and make the movements of the camera using the directions. So my job was done, not fully because we didn't get to read the data from the Oculus Rift, but an alternative was made. As I was saying before, that my part was to code this for direction so that it gets the values from the Oculus Rift, so that when the user is looking left, the motor shields would actually look left, and if they look right, then the shields would look right. Same with directions of up and down. So basically, I was going to use, as I said, Linux code, but that was cumbersome for me. So I settled on using Arduino, since the Android has got a shield, an Arduino shield on the top here, where the motor shields have been connected on the pins D5 and D3. So basically, the processing was used, as explained before. That was for the directions of the keyboard to work, and an Arduino development was used as well for the shield, for the directions to be moved, for the motors to be moving. But then the processing itself was to use the serial for the keyboard. So basically, if at the moment the position is looking right, so the cameras would have been positioned on the top there, so that way the user is actually looking to the right, and if the left is pressed, the motors would move to the left and the user would be able to see whatever is on the left. Same with the direction of up, the user would go up, but with that the degrees were a bit much, but that could be adjusted in the code so that it doesn't go all the way down, but it stays somewhere there. And if it looks down, it goes back to the center position, and on the right it goes back to look on the right. So basically that's
okay. I was connecting this to conduit to communicate so that a file can be sent through one end to another end and back and forth. So we had our first configuration on both Android, and then later on I think we had a problem with the second Android, so that needs to be flashed and reinstall all the programs. So my partner James had to take it home and do the configuration. After the network issue, I have to jump to Wesley, who is working on the motor. So I help him get those files, and we have to install a software called processing. So we had the codes from the internet, where we made amendments to it to allow the keyboard to interact with the motor, the pan tilt motor, so that when we press the keyboard arrow keys, arrow facing the top, up arrow, then the tilts up, down tilts down, sideways, left and right. So that was what I played in the project.
Brilliant, thank you.
Hello, my name is James, and I'm the network and Linux guy of the group. I'd like to quickly talk to you about the roles that I've taken in this project, and then I'll move on to the file transfer that has been created to transfer files between the two Odroids. So my main roles of this project were to do any installations of Linux on the Odroid devices using the DD tool. I then installed any drivers that were needed, installed various libraries onto the Odroids, and just generally helped out with any Linux problems that anyone in my group had. I helped set up the network for the Odroid with George, and I've just attempted to create multiple scripts to actually transfer the files over, and this is the actual concept and what I've come up with to transfer files. So let me go into this. Alright, so the way the program works is that you've got two Python programs, a client and a server. The Python client, which is shown here, all it does is it sends one file to the server, and then that picks it up and drops it into the image folder, which Martin's program, the OpenCV program, will pick up, and then whoever's in there will do whatever it wants, I guess, with it. So the actual client is wrapped in a bash script, and the way this works is the bash script will check the directory, and then if it finds a new image, it will send it over to the server and then write that image. It will keep checking and then sending until you turn it off. It will carry on doing it. If there's nothing, if it doesn't find anything, it will just wait. So that's pretty much how it works. I will now demo this program. Thank you very much. Hey, it's James again. I'm going to show you the two scripts I've got and then demo them. So this is Python get, or pyget, which receives data through a UDP stream, and this is PySend, which sends the data through the UDP stream. And just very basic client server sockets. So let's get to the demo. If I just set up the server here, and if I set it up here as well, send a file. This is the files that we've got open already. So if I if I just put that there, and you should be able to see it. Alright. Okay, so if I send hyphen to HiSend images / image 7, which we don't have, image 7 appears. Again, if we do image 6, obviously have to create the process. Send it again, image 6. It's fairly basic. Both of these would be wrapped with 2 scripts which have been created. This script wraps it in a while loop, and the second script just monitors for files in the image directory and automatically sends it. That's basically the program. Thank you very much.